Well, this teaching unit is about the technological approach of Giswater. We will explain in more detail what is this software about. In the first place, we are going to see the technical approach of this tool, then the main characteristics of the software with which it interacts with EPANET Stormwater Management Model and HEC-RAS. We'll also speak of the released versions of Giswater. We'll also see the structure of the database for the programs from EPA, as well as the basic structure of the database of pre-SDF. Finally, we will give details of the Giswater community, how it is articulated, and which are the lines of work of the association to guarantee the continuity of the project. Giswater is a driver that connects any geospatial database with any program of hydraulic analysis that is necessary. For the present, the current version 1.1 of Giswater is able to connect to the geospatial database PostgreSQL with the programs EPANET, EPA Stormwater Management Model, and HEC-RAS. The potential to have the data in geospatial database is enormous, as this will be discussed ahead. However, note that any GIS, any technology of GIS that has two suitable drivers to connect to PostgreSQL is a valid GIS for this project. Therefore, we can see here the GIS that can visualize and edit information. GVSIG, QGIS, GRAS, TerraView, UDIG, all these GIS can be used with Giswater to connect to the hydraulic simulations programs. But the project does not end here. As the information is stored in a database, it's very easy to connect to mobile devices. Therefore, we have all the types of technology fields such as tablets, PCs, Androids, or more sophisticated tools with GNSS which are able to send data in real time so that the information in the database is correctly captured. A database is also the natural environment for programs of enterprise resource management or otherwise ERPs. There are also some open source examples of such technologies like Triton and GSAN. Additionally, technologies for map publication are usually linked to the geospatial databases. Consequently, if we have the information properly structured within our geodatabase, we will make it easy to share this information and to use other technologies like GeoServer, MapServer, and OpenGeo to publish data, to share information within our organization, or to share it through internet with everybody. And finally, the SCADA technologies. Automatic field elements that capture data carrying information. These are technologies that in their natural form use the databases like elements on which they pivot. Consequently, if the database already exists, we can also integrate a full management system also in our database. This is the global technological approach of Giswater project. A single driver that allows all these technologies to pivot around the database and implements the integrated management system in the water cycle. Giswater is a project with a very ambitious objective. Its evolution, slow but safe, allows us to affirm that at this point in the version 1.1 the water models with which are compatible with Giswater are EPANET, Stormwater Management Model, and HEC-RAS. The EPAs for exchanging information and webcams. HEC-RAS is only available in pre-RAS option. Furthermore, the software of GIS that of natural and automatic form qualify the tool is QGIS. Obviously, if you're a regular user of GVSIG or UDING or ArcGIS, you can perfectly configure in your preferences your project templates for these softwares and the tool will work. The technology for database storage is Postgres with its geospatial extension PostGIS. In the future, other database technologies can be used, such as Oracle, Spacelight, but at the moment, it is only qualified to function with PostgreSQL. And finally, the operating system on which the tool works is Windows 7, Vista, or 8. It will be a pleasure for Giswater team to be able to also provide versions for Linux. In fact, being a Java cross-platform environment, this is possible with a certain ease. but the maintenance of diverse versions of Giswater in parallel is a task that at the moment the Giswater team has no guarantee. As the project grows and matures, evidently, versions for Linux are going to be released. Moving on to the topic in hand, what is EPANET? Well, EPANET is a design software for potable water networks. Its main characteristics are: it does not place any limits to the size of networks that we have to analyze, and in addition, when it is programmed in C, its code makes it extremely fast. EPANET models pumps working both at constant and variable speed. In addition, the energy consumption and the cost of pumping energy can be calculated. It can enable any form of storage tanks, i.e. diameter can vary with height. It can consider multiple categories and multiple demands in the demand nodes, besides modeling the independent pressure consumption that live through the emitters. This can be sprinklers or fire hydrants. EPANET incorporates in addition a very robust and trustworthy water quality model that is allowing us to evaluate, for example, the age of water throughout the network or to model the reactions within the fluid or at the pipe wall. This will allow us traceability of pollutants and to know the degree of involvement of different water sources with different qualities and how they can interact with our system. Stormwater Management Model, or in shortcut EPA SWMM, being the twin of EPANET, will have similar characteristics in the areas of knowledge in sewage and urban drainage. Thus, the size of networks that EPA SWMM is capable of calculating is limitless. In the same way, if programmed in C, the calculation speed is extremely fast. We can model all types of conduit shapes, both standard and non-standard ones. If the shapes are not included in the catalog, it is not a problem. We can create by means of transects and customs the closed or open sections that we want. In addition, the hydraulic model allows to incorporate external input flows and water quality. It allows us to model in 3 different ways. Obviously, the kinematic wave will be used for networks that are in the full normal flow value. The dynamic wave will be used for networks with pressurized flow. The steady-state modeling is to be used in special circumstances, since the potential of EPA SWMM is to model a variable regime. In addition, it incorporates dynamic control rules that can be user-defined so that you can interact with the network in specific circumstances, incorporating elements that can vary over time. Even though it's a rainwater model, it incorporates volumes in the dry weather flow. These are continuous inflows that reflect the contribution of wastewater from sanitary sewage and sewer systems or base flows in pipe. Consequently, it's perfectly valid to calculate sewerage networks. And finally, it also incorporates a model of pollutants in which it is possible to determine how the pollutants accumulate in an area, how they are cleaned by rainwater, how they are incorporated to the network, and how the network is transporting these pollutants, or how they will be reduced. It is necessary to point out that the model of pollutants is very difficult to use since it is very hard to calibrate it, whereby a model of pollutants in EPA SWMM will only make sense if we are able to calibrate those results. And that's a complicated task, but it does not matter because if we remained only with normal volume flow and rainwater flow, it is a calculation model perfectly valid to calculate all our networks. And we're already in the HEC-RAS section. This is a program that models the hydraulics of water flow through natural rivers or other channels. Up to version 4.1, it is one-dimensional, that is to say, it only works in one dimension. I must say that from version 5, HEC-RAS incorporates a two-dimensional model where it is possible to evaluate and analyze fluid planes in 2 dimensions. This program is developed by the U.S. Army Corps of Engineers to manage rivers, ports, and other works under its jurisdiction. Well, as we've said above, Giswater is a very ambitious project, but up to date we release versions that can be downloaded from the download section of the Giswater website. It also incorporates the project of QGIS, the database PostgreSQL, with its spatial component PostGIS as reference. Well, we will now speak about the database structure for an EPANET project. First of all, we are going to define a catalog of materials, a table where we will have the information of the material. Next, with this table already defined, we will be able to create the tables for the ARC and Node layers. These are the most important layers of the project. All the database technology, all the technology of Giswater, both for EPANET and EPA SWMM, is built based on this concept, the ARC node topology. All the network elements are going to be arcs or nodes. From here, we can define curves. The most usual ones for EPANET are patterns. These are patterns of demand, and from the structure of topology ARC node, all the elements that are nodes are going to be reservoirs, junctions, and tanks that are the elements of any EPANET project. In turn, the ARC elements are going to be pipes, pumps, and valves. Evidently, they are the same ARC elements or links that has a project of EPANET. In addition to hydraulic modeling, EPANET is capable of incorporating information of water quality, emitters, reaction sources, mixing, energy. Obviously, the data schemes of EPANET within Postgres is going to incorporate all the information so that this is fed towards the program of EPA. Once we have created all the information, we are going to choose what sector we want to export from the model, because an important thing to mention in this point is that all the information of a network will be structured in sectors so that we can export one or several sectors to a mathematical model. This is going to ease the process for faster speed in the calculation, since it is never going to be necessary to export an entire network. We can simply export the sector that interests us. Obviously, sectors must have a condition that is hydraulically coherent with the EPANET, as well as they must have the appropriate boundary conditions in order to have an effective simulation. This is due to the fact that if we send a sector to simulate in EPANET, for example, if there is no reservoir, evidently the simulation is not going to work. Thus, if we can define the sectors to be hydraulically coherent and the boundary layers to be valid for EPANET, we can define more sectors and export them all at once or one at a time to the mathematical model. To export, we define the tables of options, time, and record, and we simply execute. The calculation engine of EPANET that is incorporated in Giswater starts and calculates with these options, times, and results, and gives the information to us in a catalog of simulations. We can perform n times this operation. We will be incorporating and storing different simulations all in this catalog. If we want to visualize this information that is stored in the tables ARC and Node results, the only thing that we will have to do will be to activate the simulation selector to be able to visualize in our GIS project the simulation that we have. We will now see the database structure of EPA SWMM. Like in the case of EPANET, prior to the ARC node structure, we must define the ARC catalog where we will be incorporating the information of ARCs, a catalog of materials where we will have the information of the materials of the conduits, and with this information of tables, ARC and materials, we will define our structure, our ARC node network topology, and from there we can continue with tables of information associated to curves, time series tables, or demand patterns. Once we have the curves, time series, and patterns that are not mandatory, since a project of EPA SWMM does not have to incorporate them on a mandatory form, we can now define all node elements such as junctions, outfalls, flow dividers, and storage units. Our system needs to have an outfall and a junction at least. On the other hand, the ARC elements that we are going to have are the same as in the mathematical models: conduits, pumps, orifices, which are a type of overflows, weirs, that's another type of overflows, and an outlet that is a mathematical function that also has an overflow behavior. Once all the ARC and Node elements have been defined, we are only left to complete the data modeling of the database with the information that is necessary: climatology, groundwater, pollutants, land use coverage, inflows, wastewater, or unit hydrographs. Once we have done all these, we only need to incorporate the rain gauge to the network, linked to a drainage basin that is associated with nodes, subcatchments, and we can select the sector we want to export. Like in EPANET, that the sectors must have hydraulic coherence, they must have valid connections, that is to say, we must have a rain gauge, we must have an exit in order to allow the program to calculate and return the result. If the sector meets this condition, it can be 1, 2, 3, or 40 sectors that can be selected, and it is only necessary to define the calculation options and the result options. The information is sent to EPA SWMM so that it can be executed. The results are stored in the simulation catalog, where we can store as many simulations as we want, and once this catalog of simulations is operative, The results are stored based on if they are results for arcs, nodes, or subcatchments. We will now see the database structure of HEC-RAS. In this case, the conceptual model is completely different. While we have seen for both EPANET and EPA SWMM, the model is two-directional. You can manage all the data within the database. The information is stored within Postgres, the mathematical model is fed, and for instance, this becomes a two-directional model. In the case of HEC-RAS, at the moment, we are only at the pre-GRAS stage. For instance, we can only import a geometry into HEC-RAS, but under no circumstance the results could be returned to Giswater. Anyway, HEC-RAS has a very powerful tool to see the results of post-processes, and it does not make any sense at the moment returning the data back to Giswater. The technological approach is as follows. We have a raster layer of the digital terrain model, which we will add the river, the flow paths, the banks, and the cross-sections of the river. This will generate the necessary elements to create a 3D model of the river in a DEM standard model file that is compatible with HEC-RAS. Finally, some brief comments on the Giswater community. The project was started under protection of the Polytechnic University of Catalonia and the company BJ Open GIS Solutions, which has already become an association, the Giswater Association, which has as an objective to ensure the survival of the project. The association is creating the necessary mechanism to ensure these objectives and more specifically, the development team. Note that there is more and more participation and collaboration agreements have been signed with different entities. Also, there are different communities such as thematic, linguistic, or geographic, where they involve with different work groups. Finally, I invite people to create work groups and to create tools so that everybody can find a place in this project. And well, we came to the end of this teaching unit on the technological approach to Giswater, where we have presented the technological vision, the strengths and weaknesses of the program, and how it's structured as well as the community to guarantee the survival of the project.